Hello everyone, welcome to my channel Hypermesh Basic to Advanced. So to give a bit of a background about my channel, I make videos related to FEA and Hypermesh. So if you are new to this channel, consider subscribing to this channel if you are interested in these topics to get regular updates. And if you are already following this channel but not yet subscribed, kindly consider subscribing as this motivates me to make more videos, right? Okay, so moving on to today's topic. So in today's topic, we'll be performing a global versus local analysis, right? So first of all, what is global and what is local analysis, right? So what we mean by global analysis is when we perform an analysis at a assembly level, a main assembly level, then we call it global analysis, right? So global analysis at a global level or assembly level. And then if you perform the analysis at sub-assembly or component level, it's called local analysis, right? So what is the use of this global versus local analysis, right? Like why is it needed? So see what happens. Suppose we have a aircraft, suppose. So what happens for the low boundary conditions of the aircraft, we basically have the loading on the assembly level, right? So we have an aircraft flying, will know it will fly at certain speed, certain altitude. Because of that, there will be certain lift on the wings or whatever it is, right? So we have the loading at the assembly level. We don't have the loading at the sub-assembly or the component level, right? So there might be certain n number of components, right? Like 50, 60, 100, maybe thousands, who knows, right? So there are many components inside the aircraft, so they will also experience this loading, right? But we only have the loading at the assembly level, right? So we don't know what is the loadings at the component or sub-assembly level. So how do we derive it? So for that, we have this what you call uh, global versus local analysis, right? Okay, so we'll be performing the global analysis first, and then we'll go to local analysis to see the reaction forces, right? So how will the reaction forces come, right? So for that, for in this example, we'll be applying a load on this green component, right? So this green component is connected to this rod, right? So there will be some reaction in the rod, and this rod is in turn connected to this bracket, which at this interface, which there will be some reactions, right? So this is what we are going to see. What are the reactions generated, right? So if you can see my screen here, okay, so this is the assembly, this is the bracket, we have a rod here, right, and a green part at the center on which we'll apply the load. So I have meshed this model using 2D shell elements, if you can see here, right? So I've used mixed type elements, right, for meshing. Okay, so I already have meshed the model, right? So next, what is the next step? So we'll be creating materials in the next step. So steel is the material here, right? So I've used steel as the material because it's a default material. It's easy to use, solve the purpose for this tutorial, right? So I'll be using steel here, right, as the material. The values are present by default in Hypermesh, right? Okay. So after this, we'll be going to making the property, right? So I have made two properties here, right? So both are P-shell properties, right? And one has a thickness of 2 and the other has a thickness of 5. So just in case you have stumbled upon this video freshly and you don't know anything about Hypermesh, what are these properties, materials, load collector, load steps, components, whatever it is. So you can just check out the other videos on my channel, and as well you can check out the my blogs, right? So I'll be pinning my blog post link in the description. You can check it out there, or I'll pin it in the comment section also. You can just go and check out and read through my blogs. You will find details on this properties, materials, load collector, load steps. You will understand what are these used for, and what type of property or material to use for what type of analysis or what type of structure, whatever it is, right? Okay, so we have the property. I've created the properties, right? I've created the materials, which I showed you. It's steel. So next we'll be assigning this material and properties to the component. So here we have the components, right? So here we have the side bracket, if you can see. So I have assigned the steel property and I have assigned it a property with thickness 5. For the center and the rod part, we'll be using the property thickness of 2, right? As you can see, I've used 2 thick. For the rod also I've used 2 thick, right? Okay, so we have created the mesh model. We have applied the material and properties. So apart from this, I've created 2 RB2 elements also, if you can see here. So one set of RB2 elements I've created for constraining the 4 holes on these brackets, right? And one set of RB2 elements I've created to apply load on this green part, right? So this is all what we have created, right? So next, what we'll be doing is we'll be creating load collectors, right? So we have load collectors here. As you can see, we can go to constraint. I've already created a load collector called constraint. So in this, what we'll be doing is we'll be constraining master nodes of these RB2 elements of these 4 holes, right? And we'll be constraining all the degrees of freedom. If you can see here, 1, 2, 3, 4, 5, 6. I've constrained all the degrees of freedom, right? So just in case you're imagining how to create this constraint, for that you can go to analysis, right? And you can go to constraint, and you have to select the node which you want to constrain, and you can select all the degrees of freedom which you want to constrain, and then click on create, right? So it will constrain all the degrees of freedom of that node. So after that, we'll be creating a load, right? For that also you can go to analysis, you can go to forces, right? And you can select the node on which you want to apply the load. So in this case, I've applied the load on this master node of this RB2 element, right? And I've applied a force of magnitude 1800 Newton. So, okay, let me just hide this load, right? So you can see I've applied a force of 1800 Newton, right? In the negative y direction, right? So we have basically meshed the model. We have the materials and properties in place. We have created the load collectors and we have the load step, right? So next we'll be creating the load step. Yeah. So I've already created the load step, right? So for this tutorial purpose, I've used a simple load case, right? Analysis type, linear static, and in the SPC field, we'll reference the constraint load collector, right? As you can see here, and with the load field, we reference the load collectors, right? So we have the mesh model, we have the material, we have the properties, we have the load collectors, defining the boundary conditions, and we have the load step, right? So this is all, right? Or should we do something more, right? So what is going to happen is we have to do some extra steps to extract the results, right? So no doubt this will complete the analysis if we run it now, but we won't be able to get the output which we want, right? So for that we need to create some cards. As you can see here, I've already created some cards. So we'll go, so you can go to global output request, right? So in this global output request card, so we are selecting displacement which we want, right? Then we'll be selecting GP force output request, right? So we are requesting the output for GP forces. So what are GP forces? GP forces are grid point forces, right? So we'll get the grid point forces, that is the forces on the nodes, grid points, right? So we'll are requesting the output for grid forces, GP force. Next we'll be asking for SPCF, right? So we'll asking the output for this, and then stress as usual, right? So these are the 4 things for which we will be taking the output, right? Displacement, GP force, SPCF, and stress. After this, we'll create 3 outputs, right? So one will be H3D, one will be HM, and one will be OP2. So if you have followed my previous videos or tutorials, so you must have noticed that we generally get output in H3D, right? So in this tutorial, we are taking two additional ones, right? So we are taking a OP2 and HM, right? So we'll just see in later on this video what is the use of this, right? So next we have created a parameter card param, right? So for that we'll just go down, and here I have selected auto SPC as no, right? And then I have selected inertia relief as -2 and your post as -1, right? Okay, so this is all, these are all the cards which we need to add before running the global analysis. Okay, so we'll go through the process once more. We have the mesh model, we have the materials, we have the properties, we have the load collectors, we have the load step, and we have the cards for the respective outputs, right? So then we'll just perform the analysis, right? So for that we can go to analysis and we can go to Optistruct, and here as you can see the export options will select as all, run options will select as analysis, right? And memory will keep as default, right? And we can just click on this Optistruct button and the solver will run, right? So I'll just be clicking on this Optistruct and we'll click on yes, and we'll see the result. So once you click on the Optistruct button, right, so a pop-up window like this will open, right? So here if you can see there's a message for the job analysis completed. Here messages will be displayed. Analysis was completed, so there was no problem encountered, right? So after this we can just go to the results button to view the results, or we can just go to the tab adjacent to this view and we can view the output file also from this drop down, right? So but for our purpose we'll be just viewing the results, right? So I'll just click on this results button and we'll see. So once you click on the results button, a hyperview window like this will open. So this hyperview window basically shows us the results. So if you can see on the screen here, we have the assembly here, right? And we have the displacement legend color coded here, and which are the colors are displayed on the assembly. Okay, so we can just play the animation also if you want, right? So you can see the front formation here, right? You can see it's moving. Okay, so this is for the displacement. If you want to see the stresses, you can just go to a drop down here and we can select the element stresses from here and we can just click on apply. You can see we have the element stresses, right? Okay, so this is how we perform a simple linear statical analysis at assembly level. Now, as I said, we will extract the reaction forces and the interfaces for the bracket. So how do we do that? So for that we will again go to Hypermesh to view it, right? Okay, so we are again in Hypermesh. So what we'll be doing is we'll see what are the reaction forces on the interface of this bracket and rod, right? So for that, first of all, we can just hide the rod component, right? So components, right? We'll hide the rod and we'll hide the center part, right? Okay. So to view the reaction on the interface on this inner face of the bracket, you can just go to post right here. You can see here post, right? We'll go to post, we'll go to free body, we can go to force here, right? You can see. Then here what we have to do is we have to select the .op2 file, right? .op2 or .xdv file which is generated on the run, right? If you remember, I told you we'll be extracting three outputs, H3D, HM and OP2, right? So that OP2 file was needed for this purpose, right? So this OP2 file we'll take from here, and then we'll select the load case, like load step which we have used. That load step will be the load step defined for the global analysis, right? You can select the load step here after you import the OP2 file, right? And then you have to select the element set. So what is the element set? Is the elements on which you want to see the reaction force, right? So just click on the element set and you can select the set from here, right? And then you can create on accept, okay? But I've already imported the load, so I'll not be clicking on accept, right? We'll just close this, right? Okay, so fine. So after that, once you do that, so you'll be able to see all the loads. Let's see for that and just go to load collector to all. Okay, right. So if you can see here, these are all the grid point forces which are there, right? Due to this 1800 loading on the assembly level, right? So if you see here, so basically I'll just zoom in. So there are some movements here, and then there are some forces here, right? So this is basically how you can extract the reaction forces at the interfaces, right? So basically this is how you can extract it. And then if you want, like I'll tell you, then if you want, what we can do is basically you can perform a local analysis, as I said. So what will be the local analysis in this case? In this case, you'll be performing a local analysis on this bracket, right? So the analysis performed on this bracket will be a local analysis with respect to its assembly. So for that, how will you perform that? So for that, you can just go to the load collectors here, right? So if you see the load collectors here, so the constraint and the load were the load collectors which we had created, if you remember, in the global run, right? And these are all the load collectors which are derived basically from the global load case, right? So derived as in, what we have done is we have applied a global load, and these are the reaction forces which are a result of that global loading, the 1800 load, right? And the constraint, right? So basically for performing the local analysis on the bracket, what you can do, you can just go to the load step, and instead of referencing the load under the load field, you can just select this. I'll just show you. Yeah, so instead of referencing the load which we had referenced in the global case, you can reference this FBD F load, right? So how you will know which to reference, right? So you will be referencing this one because this has the card image load add. So what is load add? Is basically it's a summation or combination of all these loads, right? Loads, right? So this you will reference it here under the load, right? Just so under the load field, and then you can perform the analysis, right? So then you can check what happens to the bracket, and you can just vary the thickness or properties under these loading conditions and select which material is better, what thickness is better, whatever, according to your design purpose, right? So basically this is how you do a global and local analysis. I have not done the local analysis. I would need to run this again with this loading. I'll leave it up to you to perform it and try it on your own and see what happens. And you can just select some other material also and some other thickness also, and you can just play around with it and see what happens, right? Which is a better material, which is a better thickness, and whatever you want to see. Okay, so basically this is all for this video. Hope you liked this video, hope you understood the purpose of this tutorial. So thank you for watching this video, and if you like this video, please like, share and subscribe, and don't forget my social media channels, right? As in this channel, my Instagram page, Facebook page, And you can also check out my blog, right, which I'll pin in the description as well in the comments to understand more about these topics, right? So, okay, so this is all. Thank you and see you next time.